Both inside and out of JILA, physicist Eric Cornell's name stands out as a giant within ultra-cold atomic, molecular, and optical, or AMO, physics. Cornell is both a JILA and NIST, or National Institute of Standards and Technology, fellow and a Nobel Laureate, having been awarded this prestigious prize in 2001 for his groundbreaking work on the Bose-Einstein-Condensate, or BEC. Cornell's work has opened new pathways for research in quantum mechanics, offering profound insights into the nature of matter at its most fundamental level. His contributions have paved the way for advancements in quantum computing, precision measurement, and much, much more, reshaping our understanding of the universe. In today's episode, we'll dive deep into the story behind his Nobel Prize-winning discovery, uncovering the moments of inspiration, perseverance, and collaboration that led to one of our time's most significant scientific breakthroughs. Cornell will also share his insights on the current state of physics research, the exciting frontiers of quantum mechanics, and the innovative research he's currently involved in. We'll discuss the importance of interdisciplinary collaboration in pushing the boundaries of what's possible, and the role of creativity and innovation in driving scientific discovery. You'll also hear from one of Cornell's current graduate students, Anzhou Wang, as he describes what it's like working with a Nobel Laureate to push the boundaries of physics deeper into the quantum realm. You're listening to Humans of JILA, a JILA podcast focusing on the human narrative of the institution's researchers. I'm your host and science communicator, Kenna Hughes Castleberry. Every month, I tell the story of a researcher or a group within JILA, showcasing the human sides behind the science. If you enjoyed today's episode, please like it on our YouTube channel or follow us on Spotify, and be sure to share with your friends and family. This episode features an interview with Dr. Eric Cornell, a Nobel Laureate, JILA Fellow, and NIST Fellow, who studies the smallest dynamics within the quantum world, along with graduate student Anzhou Wang. So whether you're a seasoned physicist, a student of science, or simply curious about the mysteries of the universe, join us for a fascinating conversation with Eric Cornell and his team, whose work continues to inspire and ignite the imaginations of people all around the world. Let's begin our story. Thank you, Eric, for joining me today. I'm going to get started with these questions. So the first one is kind of a more broad question about, who have your mentors and major influences in the field of physics been, and how have they shaped your approach to your research?
I've had a number of wonderful mentors over the years. I think behind any physicist who's had any sort of measure of success, there's always been some important mentors. For me, I can go back to even back to high school, where I had an excellent physics teacher, and beyond that, he was the coach of the swimming team I was on. So he was not just a mentor, but a little bit of an authority figure. You know how coaches are. And I very much respected him and thought I learned a lot from him, and I admired his sense of humor and sense of sort of playfulness, the idea that physics is a fun thing to do. Beyond that, both in college and in grad school, I was fortunate enough to work with some very talented people. My graduate advisor, Dave Pritchard, is just a wonderful guy and a very thoughtful physicist with sort of a quirky way of thinking about things. And I picked up from him this idea that you can think about a given problem many different ways. That's a useful thing to have. Postdoctoral advisor Carl Wyman, who's gone on to do physics education research these days, but was my sort of teammate in the early days when we were working on the early days of Bose-Einstein condensation. And he was very influential, showed me how to think about how to do physics as easily as possible, and so that you could focus on whatever was the really difficult thing and just do everything else as quickly and easily as you can, so you can get over the technical challenges as fast as you can. So all told, it's been really, really lucky in this respect. These days, I feel that I learn things from people junior to me. My students are teaching me things. I just finished reading a chapter in a thesis, and I learned all sorts of stuff I didn't know. And so that's always good to feel that it's not just a one-way street.
Yeah, lifelong learning, right?
Yeah.
Absolutely. Well, I'll go into the next question, which is about the Bose-Einstein-Condensate, which is When people think of the BEC, they think of you quite a bit. You tend to be associated. So could you maybe explain a little bit about what that is and why it's important?
Yeah, Bose-Einstein-Condensation is a phenomenon that was predicted way back in 1925 by Einstein and Bose. Surprise, those two came up with the idea. At the time, it was not really technologically possible because it required temperatures which were too low to get to. So it took 70 years until physics experiments and technology caught up with them. And that was for Carl Wieman and I in 1995, and shortly thereafter, Wolfgang Ketterle. The idea is to get things extremely cold, and as things get colder and colder, they act less and less like particles and more like waves. Physics, we talk about classical physics and quantum physics, and cold is a way, ultra cold is a way to make the quantum physics pop, to make the quantum physics important. And as things get colder and colder, they get wavier and wavier, and if you can get a gas cold enough, the quantum wave of one atom overlaps with the quantum wave of another atom, and then you get a sort of quantum identity crisis, and you generate this sort of goopy fluid, which is known as a Bose-Einstein-Condensate. At the time, to do that, we had to reach the world's coldest temperatures.
Right.
And at that time, it was a couple hundred nanokelvin. And so we were able to make that work. And the reason it's important really comes back to this idea of quantum mechanics. It's making things very cold is a way of making quantum mechanics jump out at you and become very obvious, and the dominant effect when you're studying an experiment. In terms of importance, most things in the world aren't that cold, but a lot of things in the world that we really care about are very cold. Very small transistors, very small machinery, things like this. And so it's very important to us technologically, commercially, to understand the science of the very, very small. So really, Bose-Einstein condensation being all about the cold is a way of helping us learn about quantum mechanics without going all the way down into the world of the very small. Kind of just like a microscope, it amplifies the effect of quantum mechanics to a scale where we can see it almost with our bare eye, really, and in this way learn more about it, which will become useful for more sort of technically relevant things in the future.
Wow, that is really important because we don't understand quantum mechanics quite a bit. It's very confusing.
Yeah.
So I know that discovering the BEC was forever ago for you, but
Yes.
Could you kind of take us back into that moment of what you felt when you realized that you had made this happen?
So it was in the spring of 1995. We had recently come back from a conference, and we learned at that conference that although we were the leading group in the effort to see Bose-Einstein condensation, there were several other groups that were nipping at our heels. It was a very competitive situation. So we were feeling stressed. We were working very hard. Sometime in June or something like that, we came up with the last few critical ideas we need to make it work, which we implemented very quickly in a matter of just a few days. And when we tried it out, it worked. And it really only took, oftentimes when you first see a physical phenomenon, you have to study it for months and months and months before you're convinced it's real. But in this case, it was just so perfect. So very, very convincing that it only took us a day or two to come around to thinking, yeah, this is real. And it was extremely exciting. I remember late that night, sort of, just lying in bed saying, like, oh my goodness, this is going to be a big deal. And the timing was great because we were heading out to give to two different conferences in Europe only really literally just a few weeks later. Wow. And so we were able to present these results, which were absolutely brand new, at these conferences. And so it was a very exciting time. And I remember on the flight home from Europe, Carl and I were on the same airplane, and we were both working on the paper at the same time, and we were walking up and down the aisle of the airplane and passing each other drafts and things like that.
Marking them up and saying,
Yeah.
no, this section goes here.
Yeah, exactly.
What a wonderful kind of memory to think back on.
Yes.
So kind of segueing into what you're currently working on.
Yes.
So could you tell us a little about your current research and what you're looking at?
These days, I no longer study ultra-cold atoms. Ultra-cold atoms remains around the world a very big field of research. Just that I felt that as I was coming up on 30 years, it was time to try another thing. And in fact, even now, for a decade or more, I've had another project which has been ramping up, which is to study the electron, the humble electron, which is a very, very well-studied particle. There is, as near as anyone has ever been able to tell, it's a very symmetric particle, by which I mean the North Pole and the South Pole are just exactly the same. The electron's very different from the Earth. You know, the Earth, the North Pole, there's sea ice, and the South Pole, there's mountains. There's polar bears in the north and penguins in the south. If you were to plop down on the pole, you could very quickly figure out which one you're at. Whereas the electron, the North Pole and South Pole, except for one being north and one being south, are all pretty much indistinguishable. But there's this idea that they shouldn't be exactly the same. And there's these theorists who think deep theoretical thoughts about particle physics. And they say, you know, we think if you look closely enough, you'll see tiny differences. And there's reasons for that. And so that's what we've been working on, is to study, is it possible that the electron is not so much round, but a little bit egg-shaped, you know, kind of fatter on one end, you know?
Yeah. So how do you end up kind of determining that?
What we do is we put the electron in an electric field, and if it's egg-shaped, it should wobble, basically, and sort of fall over, and then we look for that wobbling. Just like if you put an egg in a gravitational field, it'll wobble and fall over, and we're looking for that wobble, fall over motion as we in the presence of an electric field. And we detect it using lasers, very sensitive lasers, and in order to make the effect as large as possible, we want a really big electric field. We weren't able to make a big enough electric field just, you know, you might think in the lab, well, I'll just take two pieces of metal and I'll put a big voltage on them and I'll have a big electric field in between them. But if you do that, you just get sparks. You can't get up beyond a certain electric field. Turns out the largest electric fields in nature are inside molecules.
I see.
Think about salt. You know, you may have learned in high school chemistry that salt is sodium chloride, and the sodium is positive and the chlorine is negative. You can imagine that right in that tiny space inside the molecule, inside the salt molecule, between the positive and the negative, there'd be a very big electric field. And it's true. We don't use salt, we use another molecule, but that's where we get the world's largest electric fields. And that's where we get the very highest sensitivity. The electrons float inside that space inside the molecules, and we measure the wobble right there.
I see. Wow. How fascinating. Kind of a broader question for you is, how has the Nobel Prize affected your research and your career in science?
You know, seeing Bose-Einstein-Condensate really affected my career in a big way. At the time, I was essentially a junior professor, you know, assistant professor, and going from, you know, we saw Bose-Einstein-Condensate, it went going from, you know, standing beside my poster in the big conference hall with no one wanting to talk to me to giving the keynote address at the conferences, really? You know, almost overnight. I mean, literally just in a few months. And so that was a very big difference in my career. It became easier for me to get my grant proposals funded.
Yeah.
Instead, winning the Nobel Prize was less of a big difference, you know, in terms of like really a big step, because I was already, at the time I won the Nobel Prize, pretty well known in physics and was able to pursue my funding and attract strong students. So many things were going my way. It was very nice to win the Nobel Prize, but it didn't change my life that much. I mean, for a year or two, it was a little bit like, you know, becoming Miss America or something like that. You have to take sort of a victory tour. You go around and
lots of press.
Yeah, lots of press. You visit different universities and you give talks. But after a year or two, you sort of take the tiara off and pass it on to the next Nobel laureate and go back to your researches, which is what I did. And so it was nice. But I'm happy to say that things sort of went back to normal after a few years.
Sure. And so looking back kind of over your career, is there anything you would have done differently?
I don't think I would have done scientifically very much differently. I can look back now and and see. I would do experiments, and there was times when I wasted a lot of time because we were on the wrong track, and I wish I could go back in time and whisper in my ear, don't do that.
Sure.
But you can't do that. And I think under the circumstances, did about as well as I could. So no, I think I'm pretty happy with how my career has gone.
Good. Excellent. That's always a good sign to hear, right?
Oh, sure. Yeah.
As opposed to I
Yeah.
would have changed X, Y, and Z. So you being a pillar in the physics community and being such a giant in this field, what do you think is kind of the biggest challenge currently facing physicists today?
I think physicists always have to be on the alert to keep things new, to keep things changing. There can be a tendency to sort of spiral inward and focus harder and harder on smaller and smaller things. I know I'm susceptible to that. So a key to sort of future success in physics is to look for sources of new questions, new challenges. These, I think, very likely could come sort of at what we now consider to be the outer boundaries of physics, and heading off where physics overlaps with other areas. So I'm very much in favor of hyphen physics, bio-hyphen physics, chemical-hyphen physics, whatever it is, geo-hyphen physics, econo-physics, what have you. I think that's where a lot of excitement can be, where if we take the basic tools of physics, which are really a highly simplifying way of looking at the world, and apply those sort of razor-sharp tools to more complicated problems.
Yeah, absolutely. Going in a new direction. Well, my last question for you, Eric, and again, I appreciate you walking me through everything, explaining some stuff. This has been a wonderful discussion. Is what sort of advice would you give to young physicists who are entering this field, who are looking to the future?
The advice I would give to young students is I would remind them that physics has a way of changing, and especially if you're a college junior or something like that, or a first-year graduate student, the topics that right now seem to you like the most glamorous, hottest topics in physics probably won't be in 6 or 7 years. And so as you sort of prepare yourself, train yourself to become a professional physicist, to contribute your own ideas, it's important to try to remember to stay broad, to keep a wide range of interests, to follow developments in physics that seem a little outside of your area, because there's a significant chance that your particular area of physics will have sort of run out of steam in 7 or 8 years. Whereas if you've learned how your area of physics connects to other areas, how you can use your specialty to contribute in other areas, then your career, your possibilities of making progress in physics won't also dry up at the same time.
Yeah, you have kind of an extra field that you can go into a little bit.
Yeah.
Excellent. Well, thank you so much, Eric.
It's been my pleasure. This has been fun.
To get a deeper dive into Cornell's current research, JILA graduate student Anzhou Wang joins me in the studio. Thank you, Anzhou, for sitting down with me and telling me a little bit more about your research. Could you maybe start by describing your current research project?
Sure. So our current research project is a precision measurement. We focus on measuring the roundness of an electron. So naively, you would assume an electron is just a fundamental particle. It shouldn't have any internal structures. So it should, in some way, classically, should be a perfect sphere. But we believe the electron is actually not as round as you may imagine. So it's not a perfect sphere. If you zoom in, you'll find maybe it's a little bit more like an egg shape. So yeah, our experiment tried to measure basically the exact shape of an electron. And then natural question is, why do we care about this?
Absolutely.
Did we just do it for fun?
Well, yeah.
All science is fun.
Yeah, in some sense, yeah, sure. Fun is very important. But beyond just fun, we measure the roundness of an electron to to try to answer a very fundamental problem of the universe, of the physics. The question is, why is our universe made of matter instead of antimatter? Or why do we human, the Earth, exist? So we know the Big Bang happens and it's slowly evolving to the universe we live in. But if the universe is perfectly symmetric, we would expect same quantities of matter and antimatter, and they would collide each other and emit 2 photons during the Big Bang.
Okay.
So if we have same amount of matter and antimatter, the universe shouldn't exist. We shouldn't exist.
Right. So it cancels out, right?
Yeah, it cancels out.
Okay.
So it just leaves us a boring universe with only light. To make our universe exist, we need more matter than antimatter at the beginning.
Right.
So yeah, that's the puzzle physicists have. The most successful theory the physicists currently have for the particle theory is a standard model.
Okay.
The standard model actually predicts a pretty boring universe.
Oh.
It predicts a tiny little bit imbalance between matter and antimatter, which wouldn't explain the universe we live in.
Right.
So a lot of theorists are working hard to propose theories beyond standard model so that on one hand it's compatible with the current discoveries, and on the other hand it can explain why we have the matter-antimatter imbalance. And a lot of those kind of theories would have a side effect which can show up in exotic properties of fundamental particles, including an electron. And that comes back to our original question. By measuring the roundness of an electron, we kind of are measuring those side effects.
Okay.
And that can provide some evidence to see if those theories are correct or not in some sense. Yeah, that's why we care about the roundness. In the scientific term, it's called the electron electric dipole moment. So currently, our JILA-EEDM result put an upper bound of that roundness of the electric dipole moment of 4 times 10 to the minus 30 e centimeter.
Oh, wow.
So it's a very, very small number, but in some sense, if you say hand-wavingly, if you expand an electron to the size of the sun, and you scrape off a thin layer, which has a width of a COVID-19 virus,
Oh, wow.
from the North Pole to the South Pole.
Okay. So very small.
Yeah, so super thin. That's basically the roundness we are measuring.
Oh, my goodness.
Yeah.
Okay. So it's like super minimal.
Yeah.
Very precise.
Exactly. Yeah. So that's why our experiment is a precision measurement experiment. To add a little bit of science in, the way we measure the electric dipole moment is to put that in an electric field so that we can measure the energy difference. So our secret recipe to measure something this small is that we don't put the electron in the electric field generated in a lab directly.
Okay.
We measure the electron in a molecule,
Oh, wow.
which can generate a huge lever arm of this electric field. So we only need a small electric field, and then the molecule generate a huge electric field for us. Okay. Then we further measure this quantity.
Yeah.
So we're basically using methods of AMO physics.
Okay. So the molecule does the work for you.
Exactly, yeah.
Nice. Oh, that sounds like it would be way easier than generating this big field in the lab.
Yeah, also it's basically impossible. So just to put numbers here, we are only applying like tens volts per centimeters.
Okay.
And we get tens of gigavolts per centimeter back. So they have a 10 to the 9th
return.
Gain.
Yeah. Wow, that's incredible.
Yeah, that's how we can possibly measure these small quantities.
Yeah, that makes sense. You need something really big for that. So changing kind of gears here, what made you originally interested in going into physics?
Well, I would say maybe it's just I'm curious of the world when I was a kid. Yeah. I always like to read the popular science books, and maybe I behave a little bit better than my classmates in physics subjects.
Okay.
Yeah, and also I think I did a fun science project, a physics project in high school with my friends. So we studied some ferromagnetic fluid. We put it in a magnetic field to see its behavior. Yeah, and probably that's my initial moment. I said, oh, it would be cool to be someone who will work in physics, like experimental physics.
Yeah, and then you came here.
Long story short, yeah, that's it.
I understand. You did a lot more in between high school and coming to JILA.
Yeah, exactly, yeah.
So, and that kind of leads into my last question for you, Anzhou, which is, what is it like working with Eric and working in his lab?
Yeah, so it's pretty amazing, I would say. Like, you would have the opportunity to work with a Nobel Prize laureate. So, Eric, indeed, as a Nobel Prize laureate, he has great insights of physics. We literally learn a lot of physics from him. So before I joined this group, I would say I learned a lot of physics. I learned the way to calculate them. I learned how to massage all the equations. But I would say I probably don't understand the physics behind those equations 100%. And Eric is amazingly good at providing this physics picture, physics image. Actually, I don't think he do a lot of calculation himself. It's mostly our graduate student work, but he will always guide us towards the right direction. So currently, we are the only project that Eric has.
Right.
So we actually have, you can talk to him very often and discuss physics questions with him. We can basically just go upstairs and go knock on his office, and we can discuss the latest process happening in the lab, or even just ask him stupid physics question we fail to understand. Yeah. And Eric is a very enthusiastic, energetic guy. And also he has a very good sense of humor.
Yes.
Yeah, he will often just come down to the lab and he got excited. Oh, group, let's go to the whiteboard and why don't we write it down? Yeah. Something like that. It's a very cool process, and also our experiment is a very difficult experiment.
Yes.
Not a lot of people work on this particular problem, so we don't have a lot of experience to study from. So when we run into difficulties and we got super frustrated, Eric always have the magic to pull us out of the frustration and drive us to move on.
That's wonderful.
So when I first joined the group, I see Eric as like almost a god of physics because he's a Nobel laureate, Nobel Prize laureate. Everything he said about physics must be correct.
Yeah.
But actually not long after, I realized, okay, he's also a human being.
Yes.
He would make mistakes, sometimes even physics mistakes. Yeah, so that's when I feel like he's very approachable and I can talk to him more easily. We sometimes try to make fun of him. Yeah.
Good. Keep the humor in the lab, right? Absolutely. Yeah. Oh, well, thank you, Anzhou, for sitting down with me. I've really appreciated you walking me through everything.
Yeah, of course.
Thank you for listening to Humans of JILA, a JILA podcast. Be sure to subscribe to JILA's YouTube channel or Spotify channel for more information and to keep listening to these episodes. This episode featured JILA and NIST Fellow and Nobel Laureate Eric Cornell and JILA graduate student Anzhou Wang. Production design, sound design, and research by Kenny Hughes Castleberry, with assistance from JILA's Science Communication Office, Eric Cornell, and the Cornell Research Group. Sounds and music from Pixabay and Kevin MacLeod. JILA is a joint institute between NIST and the University of Colorado Boulder. JILA hosts this podcast. Any use of this podcast without JILA's permission or credit is prohibited.